myself or what?
Okay, so I feel that we can start. So it's my great pleasure to welcome Richard Mushotzky. He is the second speaker of today from the Washington, D.C. region and from the NASA Greenbelt, and he's professor at the University of Maryland. He's a well-renowned expert on AGN physics, also on ULXs and other X-ray sources. He was involved in several X-ray missions since I could mention Chandra, Suzaku, X-ray Newton, all Swift, and all these ongoing and also future X-ray missions. And who will give us an introduction to high-energy astrophysical spectra. So, Richard, it's very nice to have you here. And please, the floor is yours.
Okay, well, thank you very much for inviting me. So just a little apology, since we have a broad range of backgrounds. So this material is sort of at a more or less basic level. So some people will be learning things, other people might be a bit bored, but please ask questions. So actually, high-energy astrophysical spectra, almost a trivial statement. What is high-energy astrophysics? We should remember that this is not only the study of high-energy photons, but of the objects that are producing them. So in other words, where gravity is very strong, things are moving very fast, they're very hot or energetic, and actually even the universe itself, because we know that most of the material baryons are quite hot and basically only are visible in X-ray astronomy. And so this covers a very wide range of physics, and in this talk I'll only have the time to talk about a small number of things, while you could argue that neutrinos and cosmic rays and gravitational waves are also a part. So far we don't have spectroscopy of them, so I will focus on photons. There's been a lot of work on this in the past. I just give a list. About a decade ago, there were a set of schools at the Mullen Space Science Laboratory, and many of the experts talked about that. Randall Smith has written a nice introduction at an X-ray school. However, while there's an awful lot of information out there, I think it's not necessarily in the form that's required by graduate students, postdocs, and other non-experts to get the information out of the spectrum. In other words, there's a lot of stuff about atomic physics. These are density sensitive, but if you're trying to get down to the nitty-gritty, observing and interpreting your spectra, I detect these lines and the temperature is whatever, the density is this, and the abundance of uranium is that. It really is nothing you can grab and just use immediately. Also, for people who are studying the continuum, I'm looking at shapes of the continuum. What does that indicate about the object? Is there strong gravity? Is there relativistic phenomena? So I'm going to talk a little bit about that in the meeting. Now, of course, we all know the motto that a picture is worth 1,000 words. And of course, we all know that a spectrum is worth 1,000 pictures. Well, that's a great statement, but we have a serious problem about human beings. We are built to understand visual information, pictures. We are not built to understand spectra. In addition, at least I don't know what it's like in other places, but in the United States, the teaching of the fundamental atomic physics that goes behind the formation of the continuum in objects and the formation of lines is basically not taught very much anymore. And when I teach graduate classes, at least at Maryland, I find that the majority of students don't really have the background to understand what's going on. So we need to have specific discussion and introduction of that. In addition, I think our community has a similar problem because it requires a deeper level of understanding than analysis of pictures, if you will, or even of time series, which of course is a bit more specific. Less than 10% of the Chandra and XMM papers are based on high resolution spectra grading. Now, what you see here in the right-hand panel is a chunk of the spectrum of a very famous Seyfert-2 galaxy. Hopefully you understand what Seyfert-2s are. If you don't, just tell me and I'll explain it. But this is In black, we have the spectrum from CCDs, and in red, we have a Chandra high-energy transmission grading spectrum. And you can see the radical difference in the level of information. On the bottom, you see the identification of a bunch of these lines in linear format. The top panel is in log format. You can see the high dynamic range required. The vast majority of X-ray spectra out there are from CCDs or their equivalent, and sometimes people are still using proportional counter spectra. And so there's a real problem in information content and interpreting them. Okay, so just, I mean, it's obvious, but you know, the objects of study are things like black holes, both supermassive and stellar mass black hole, neutron stars, supernova remnants, clusters of galaxies. I should have added stars and other things. And there's a huge range of physical processes, from bremsstrahlung, synchrotron, Compton emission, coronal plasmas, etc., all the way to gravitational waves. So to try to say we're going to cover X-ray spectra is a very broad subject indeed. Of course, these spectra contain a huge amount of information. This is the information we want to get out of understanding astrophysical objects. What is the temperature of the gas, the density, the magnetic field, the gravitational field, et cetera, chemical composition? You can read the slide as well as I. And if we actually understand what the spectral features are or the continuum shapes are and try to model them, we then have an opportunity to discover new things. As many of you probably know, there's been a lot of discussion about a possible signature of dark matter in the X-ray spectra of clusters. In order to make such a claim, you have to show that you understand what the other lines are and that there's not something missing in your atomic physics or in your physical models. And again, here's just a list of the objects. I tend to repeat things so they get things. Just to remind you that there's 4 sources of information in astrophysics: photons, the image, the spectrum, the time series, and polarization. And obviously you can combine these things. And so an awful lot of the papers in our subject have talked about imaging spectroscopy of obviously extended objects, supernova remnants, galaxies, clusters of galaxies, or time result spectroscopy, obviously of variable objects, X-ray binaries, active galaxies, stars, etc. And when you combine one with the other, you have an awful lot more information, but also another whole level of complexity. And I'm not going to talk in detail about that, don't have the time, but try to figure out from things like time resolved spectroscopy, what is significant and what sort of statistic you use to determine what is significant, I think is an issue that we haven't really solved yet in the field. So just a little introduction. Basically, over a very wide wavelength range, notice I'm flipping units here, 1 angstrom to 50 microns, atomic processes dominate. In other words, the spectral features, both the emission and absorption, are produced by atoms. And of course, the continuum is also produced by atomic processes, things like bremsstrahlung or Compton scattering or synchrotron. Now, in the infrared, which I'm not going to talk about, a lot of the continuum is produced by dust, which is a totally different process. We're fortunate, if you will, in the X-ray band that most transitions, not all, but most transitions are from hydrogen and helium-like ions, which have, compared to more complex ions you see in optical IR or even UV spectra, are much easier to understand. Not that they're easy. Did the screen recover or did it go out? Okay, is it back now? I don't hear anybody. Are we okay?
It was okay before, I think. Now we see the PowerPoint.
Yeah, my screen here went blank. Okay.
We can see it very well now.
Okay, good.
Mhm.
And then at energies above 10 keV, there are also nuclear processes, which I won't talk about. So if you were an optical astronomer, this is what you get out of your spectroscopy. Classical lines due to hydrogen. And like I said, we have hydrogen-like and helium-like transitions, but from heavier elements. In other words, what are heavier elements? Well, in the X-ray band, we don't see hydrogen and helium-like. Try this in English. Lines from hydrogen and helium. And basically the lowest Z element, atomic number element we see is carbon. And we see things up to nickel. This is a plot from Fritz-Perls, which shows the wavelength range of the lines from individual elements. And these are chosen to be the more common elements, which tend to have the strongest lines. And you can see we cover a very wide wavelength range of roughly 40 or 50. Now, think about this for a moment. If you're a optical UV or astronomer, in both the optical and the UV, we basically have a wavelength range of about a factor of 3. In the optical, 3,000 angstroms to 1 micron. In the ultraviolet, roughly 1,000 angstroms to 3,000 angstroms. And here, all of a sudden, we're jumping to a wavelength range of 50. That radically changes the nature of the type of analysis one has to do. So I was asked to come up with some of what I think the more important results are, and it's enormously subjective, and so I've just come up with a few of these things. For example, you need spectroscopy to map the innermost regions of black hole accretion disks using the iron K-line fluorescent complex, I should say. And one has higher resolution. The quote-unquote line is actually a suite of lines. Measurement of the dark matter, mass, baryonic, and chemical composition of clusters and groups of galaxies. One of the most amazing discoveries made a long time ago is that most of the baryons in groups and clusters, and probably in galaxies also, even though it's not quite so certain, is in the hot X-ray emitting phase. And this is also true of the intergalactic medium. In the X-ray band, we can detect and characterize the winds from starburst galaxies and active galaxies, which influence how galaxies have formed over cosmic time, one of the most important issues in all of astrophysics. The right-hand picture is from X&M observations of the center of the Milky Way. The color code is a temperature code, which shows this wind flying out from the galactic center, which goes to quite large physical scales and illustrates that the formation and evolution of galaxies is a process in which high-energy astrophysics is key. Then there are things about the structure of stellar coronae, a mystery with going way back to the study of the sun, but with X-ray spectra of nearby stars, there have been breakthroughs in understanding the corona. The same thing for massive stars, stellar winds, which are extraordinarily important in influencing the interstellar medium in our own galaxy and many other galaxies. Measurements of the neutron star properties, particularly the magnetic field. Nucleosynthesis. In the X-ray band, we can directly measure the elements created in supernova from studying the afterglow, so to speak, the supernova remnants, and understand the anatomy of how the supernova works. The process of how gas in clusters of galaxies forms, evolves, and changes due to this influence of what's called feedback, primarily from active galaxies. And then understanding how accretion works. And a particular example is cataclysmic variables, where you actually can directly measure the nature of accretion from understanding the X-ray spectra. In the right-hand panel, you see a suite of high-resolution spectra. Notice I'm not mentioning people's names on purpose, because I'm sure I would have left somebody out. So I apologize in advance to the people who've done the work. Anyhow, you see these lines, and you can see the comparison of models and the theoretical models, which don't include a bunch of physics, were in green. And the red is the data. You can see there's a discrepancy. which is a key to how gas is heated and cooled in the cores of these very massive systems. This is a simulation of what a stellar wind looks like in a rapidly star-forming galaxy. And by measuring these lines, you can get the velocity of the wind, you can get the energy of the wind, its chemical composition, its mass. And this is a key to understanding how this process of feedback, the effects of star formation and black holes, affects the growth of galaxies. This is a simulation, by the way, for the CRISM upcoming satellite. You can't do this with gratings because it's an extended source, even though you can get reasonable resolution, but not this good. Now, even objects that we don't think of as being high energy, like planets, have high energy photons. So for example, in the left-hand panel, we see the Chandra image of Jupiter, where we see X-ray emission due to several processes, aurora, precipitating electrons. And on the right-hand side, we see X-ray emission from comets, which is due to a rather complex physical process called charge exchange, which they definitely don't teach in undergraduate and graduate classes. And basically comets are, you can trace the material of comets in the X-ray band by looking at this interaction between the solar wind and the cometary gas. When we think of the sun and stars like the sun, we don't normally think of high energy phenomena, but this is an X-ray image of the sun over its full cycle. And you can see the sun glows in the X-rays. Stellar flares are extremely important, the stellar corona. And then even cold material, which gets in the way of X-ray emission in the interstellar medium of M31, allows us, if you will, to X-ray the interstellar medium in nearby galaxies. Take a deep breath. Okay, so why, since I'm trying to set up why do this at all, so one of the positive things about high energy is that a complexity that you see, especially in the ultraviolet and the optical, is the effects of radiative transfer are relatively weak, which makes understanding spectra a lot easier. We can observe these objects behind lots of dust and gas, which you can't well, you can in the radio and the X-ray, and that's the only places you can do that. From just a mere accounting point of view, most of the baryons in the low redshift universe are only visible in X-rays, either by emission or absorption. Certain classes of objects have most of their energy being emitted in the energy band. And then it's sort of a sociological statement. We have lots of objects we can study. So here's a latest example of hundreds of thousands of objects discovered and studied by the recently launched Rosetta satellite, but not so many, overwhelming. When you look at a deep optical image, you're sort of overwhelmed by objects. So we have hundreds of thousands, or hopefully when Rosetta is finished, millions of objects, which is certainly enough to keep us busy, but not enough to sort of overwhelm us. So what are the unique properties of high energy spectra? So like I said earlier, the spectra are relatively simple compared to other wavelength bands. Diagnostics of how the gas is ionized are fairly quite straightforward. Collisional diagnostics, shock diagnostics, photoionization, which is not true. The X-ray band contains diagnostic to all stages of ionization, not just the high ionization lines, because atoms that are not highly ionized can detect in absorption. So this is true. This is the only wavelength band, and this is true, where you see basically all stages of ionization, both due to cold material in absorption and hot material in emission. Like I said earlier, it covers an enormous range in wavelengths and an enormous range of ionization. It's again unique. It's sort of strange. I'll get to that in the next slide, the type of data that we have compared to other wavelength bands. What's also important for an analysis and interpretation is that you can literally measure the continuum that's responsible for the ionization of the gas. In the optical, most of the ions are ionized by photons in the extreme ultraviolet, which you just can't measure directly. In the infrared, you have tremendous issues with that the continuum responsible for heating the dust is basically extinguished by the dust itself. And so this is a really important thing for interpreting the spectra of objects where collisional ionization dominates and where photoionized plasmas dominate. I'll talk a little bit later about the difference between the two. And also, again, a sociological difference on modeling the continuum. People who study active galaxies, Xray binaries, spend an awful lot of their time and effort trying to understand what the continuum can tell us about the object. This is almost never done in the optical and UV. Just also a parenthetical remark, trying to understand the continuum is also important in the infrared thing. So a sociological issue is that while we do have a few quote unquote high resolution spectra, the resolution that we have, which is typically even high resolution is less than 1,000. In the optical and in the radio and the millimeter, resolutions of 10,000 or even 100,000 are fairly common. We just don't have that in the X-ray band. Also, we tend to have the CCD data, which is a resolutions of 10 to 50, which you simply don't have in any other wavelength band. In the optical, you either have high resolution, resolutions of 1,000 or higher, or colors, which is a resolution of 5. And so trying to compare what we do in the X-ray band and do in other bands is a little difficult. Also, virtually every type of physical process, it's just the basic ones, black body, bremsstrahlung, compensation, synchrotron, are important, which is simply not true in many other wavelength bands. And of course, we combine them all together in many sources. So another difference in the X-ray band, in addition to the mere factor of 40 for line emission, we have a factor of over 4,000 in energy, going from 0.1 to hundreds of keV. And where you transition from X-rays to gamma rays is a matter of taste. So for studying the continuum, we have this incredible bandpass. It's like going from the ultraviolet into the millimeter, which very few other things. So trying to develop models that cover this enormous range in energy for the continuum is again unique. On the right-hand side, we have a nice set of graphics that Martin Elvis developed, what would happen if optical or ultraviolet astronomers were given the same tools that X-ray astronomers were given. So in the top panel, we see colors. In the middle panel, we see what used to be proportional counter resolution. In the bottom panel, we see CCD level resolution. And of course, the gradings are better, and the level of information is quite different. Another issue is literally the basic atomic physics. If you will, the strength of lines, those of you who've had an atomic physics class, the F values are proportional to the wavelength. And so, for example, in the UV, lines from the same ions that you can see many of the ions in both the UV and the X-ray, but the UV lines are 10 to 100 times stronger, which means, of course, that they're easier to detect, but it also means that they saturate at much lower column densities. And so in the X-ray band, we can literally see denser material, which you can't see in other wavelength bands because the lines, well, you can see it, but the lines are totally saturated. So a lot of the energy, a lot of the information is missing. Another unique thing that we try to do, which I mentioned earlier, is that we try to model this entire enormous energy range. Nobody else tries to do that except the people who study blazars, who try to do everything from the radio to the gamma ray. But in order to do such modeling, you need to have a large degree of complexity because there's many, many physical processes involved. Here's a figure where people are taking the broadband X-ray spectrum of an active galaxy and interpreting it. So on the top right-hand panel, we have the interpretation, decomposition of the spectra. In the bottom left-hand side, we see the physical places that are responsible for that. And this sort of interpretation is almost unique to X-ray spectra. And one might argue that we're really being rather arrogant to feel that we can actually do this sort of thing, given the level of complexity. And of course, we have an issue of bandpass. We don't always have this 0.1 to 1,000 keV bandpass. We try to fit models inside the data that we have, but of course, whether these models fit outside the data bandpass we have is just not clear. And what we see here on the left-hand side, these authors actually have this enormous range. And what happens as they keep on making their models more sophisticated to fit the broader and broader range. And you can see going from can you see the pointer here? So going from here, where you're not fitting the high energy range, you add more physical complexity, you start to fit it, and then you also try to change your model to see which one better. And one of the big issues here is that the signal to noise varies enormously across this energy range. And if you use a statistic like chi-square, which is heavily biased by signal to noise, you may end up with the wrong result. And you need some, I'm sorry I didn't attend all of Keith's talk, but this is, I think, one of the big issues we have now in spectral fitting, how to appropriately weight the data. Okay, so these differences have led to different techniques in sociology for fitting spectra. In particular, this concept of forward modeling, XPEX, Chow, ISIS, etc., is standard. And this is simply not standard in almost any other band. We tend to do things like line ratios. We focus on statistics, goodness of fit. You'll very, very rarely, if ever, see reduced chi-square published for an infrared or optical spectrum. We tend to fit, I'll call them well-defined models, whether they're phenomenological, and I'll call them quasi-physical. They're good attempts at physical models, but of course, they're not complete. And then one ends up with degeneracies. You can have many models, but many is too strong. You have a range of models which give you the same chi-square, but how do we decide which one is correct, or correct is probably too strong a word, which one's a better attempt? And like I said, we have this attempt to fit all the data, which is quite challenging. So just to remind you, if you're talking about spectral fitting, you can break it into 2 bits, the continuum, and line, emission, and absorption. And like I said earlier, these are very strongly connected, since we can actually measure the continuum that is responsible for ionizing the gas. And we could connect these two, which are required for a full-up physical model. So simplistically, what are the sorts of things that one can learn from the continuum spectrum? Well, trivially, the physical processes responsible for photon emission. By the way, just a comment, am I speaking too fast, or is it okay? Feedback, please.
Yeah, I think it's perfect.
Okay, thank you. Because I
thank you.
Too fast at times.
Yeah, also online participants agree. It's perfect.
Okay. So trivially, the physical processes responsible for the photon emission. How much energy is in the system? A fundamental question we all want to know. How can we break down this energy budget? How much of it is in the field, particles, fields, thermal energy, kinetic energy, which again is crucial for understanding the physics here. The distribution of the particles, can they be defined by a temperature? Are they non-thermal? And we have, for example, the power law slopes of the relativistic particles in synchrotron and Compton. You can also, this hasn't been done yet in X-ray astronomy, but hopefully will be soon. There are lines that are sensitive to the magnetic field. This is done in the optical band. And there are unique lines in the X-ray band due to cyclotron features, which we can measure to get the magnetic field. And then you can get the geometrical structure of the system. Um, there are many continuum features which are like quote unquote reprocessing by disks, or the innermost radius of an object that cuts off the thermal distribution that we can get out of this. So I see there's something in the chat. I can't see the chat, so I'm going to go on. So these are the trivial statements about what one gets out of the lines. You can get the temperature of the gas, you can get its density, its chemical composition, its ionization state, and provides, notice I'm repeating, dynamical information, the nature of the emission process, what are the detailed atomic physics that produces the lines, whether the gas is in equilibrium or not. Many people make naive assumptions that the gas is in equilibrium, thermal equilibrium, statistical equilibrium. It's not necessarily true. And then we can actually see gravitational redshifts. And then, like I say, someday we'll be able to measure the magnetic field by looking at lines. So, how does one extract the information? We have to fit models that determine the shape of the continuum and determine which physical processes. And we have to have a detailed analysis of the emission and absorption lines. And just, again, I'm speaking to a wide audience. Absorption happens from gas in the line of sight, while emission happens from all gas that's within your beam. So one has to keep that in mind in interpreting the spectrum. Again, just to remind you that basically there are two classes of plasmas, hot gas, that we study via X-ray spectra. Photoionized, which means the source lights up the gas by photons hitting it. And the classic examples are active galaxies and X-ray binaries. H2 regions are regions that are ionized by stars or stellar winds, mostly photons from stars. And then these have particular range of spectral signatures, so we can distinguish whether the gas being ionized. CIE means collisionally ionized and in equilibrium. And here, the gas is ionized by basically energetic electrons running around, smashing into atoms and ions. This is basically hot gas. And the classical examples, this plasma was originally named after stellar corona. So the C used to be coronal equilibrium. Now we could talk about collisional equilibrium. Supernova remnants and clusters of galaxies. And strong emission lines are detected. And going back to your quantum mechanics, which levels change in the fundamental quantum state are favored, in other words, hydrogen and helium-like lines. Now, coronal plasmas, these can be separated into these two categories. And there are particular ions which produce the strongest lines, hydrogen-like, helium-like, and neon-like. So in other words, what does it mean? Hydrogen-like is an atom with 1 electron left. Helium-like is an atom with 2 electrons left. Neon-like is an atom, I think, with 10 electrons left. And between them, these produce the strongest lines that we see over a very wide range in temperature. So understanding them is what we need. So here's my favorite collisional plasma. This is a cluster of galaxies. It's one of the nearest and most massive clusters. In the left-hand side, in color, we see an X-ray image, color-coded logarithmically. So there's about a factor of 1,000 in intensity. And on the right-hand side, you see an optical image of the same cluster, where you see the stars, the light that we see comes from the stars and galaxies. And like I said earlier, one of the giant discoveries of X-ray astronomy is that most of the baryons in these clusters, roughly 85% of the baryons, are in the hot gas and not in the stars. So this discovery was a radical change in our understanding of the largest structures in the universe. And when you measure how the gas is distributed, the temperature of the gas is a function of position, and the strength of the lines in the gas, we can get the mass of the system, its chemical composition, its dynamical state. So this is a suite of spectra from in a hot gas due to bremsstrahlung, and a cluster is an excellent example. Some of the strongest lines and the elements from which they come are indicated. And like I said earlier, like I said, I repeat things frequently, the shape of the continuum measures the electron temperature. And so you can see a range of temperatures, and here the temperature is measured in keV, which only astronomers tend to do. Let's see if I can pull up the chat here. Okay, this is a detailed question about fitting in detector space. So what I'm showing here is a simulation, and I'm going to have to postpone this until the end. So just hold on. Hopefully Keith can chime in to help answer this question.
Yeah, we will have time at the end for discussions and questions.
So in order to interpret this, one needs the help of our atomic physicist friends. And we need this thing called a plasma code. There are thousands of lines, a wide range of cross sections and detailed processes. And so when we do our forward modeling, we have to develop a code that can predict what the data would look like. So the inputs of density, the temperature, the chemical composition. Here's a list of some of the codes. Historically, I'm sorry, I left out a code due to Neva and Castro. Right now, the bottom three, Specs, Chianti, and AtomDB, have been used as inputs to many of the fitting engines that we've talked about, XSpec, Specs, ISIS, etc. These plasma codes are continuously updated with more and more atomic physics, allowing us to fit the lines much, much better. This is a big deal when we got the spectrum of the Perseus cluster from Hitomi. We could literally see that there were problems with the plasma codes. So one of the outputs from the plasma codes is the intensity of these complexes of lines as a function of temperature. So you see that in the top panel. It's what lambda basically is the energy emitted by the sum of all the lines due to a given element called the cooling function. And you can see that these have it. This is a log plot. Notice the y-axis goes through 5 orders of magnitude. So as the temperature changes, the lines that we see change radically, and the lines from different elements change differentially, which provides a lot of information. The bottom 2 panels, we see the predictions from a plasma in equilibrium, the ionization state of oxygen as a function of temperature. And then the bottom, we see the same thing for a non-equilibrium plasma, but the variable is not temperature anymore, but it's the density and the time since, this is basically for shocked ionized plasmas, the time since basically the gas was shocked. And so if we can figure out which one of these models is correct, and we can by looking at the line ratios, we can determine things in a supernova, basically the combination of density and the time at which it was shocked. So I'm going to skip over this next slide. In addition to emission lines, like I said, we also see gas in the line of sight, and we see absorption lines. So here's Chandra grating spectra for 2 active galaxies, the names that are given. And this is focused now in energy range, not wavelength range. And it's focused on silicon transitions. It turns out that silicon has 12 ionization states that are relevant in the X-ray band. And these absorption features come from each one of those different ionization states. And you can see in these two different AGN, very, very different strengths. So notice this line is very strong here and this line is weak here, which tells us about the ionization state of the gas. And by looking at the line widths and line shifts, how fast the gas is moving. Now, when the gas absorbs, it also emits. And so here, this spectrum says the gas is almost totally in absorption, but this could be misleading because you can absorb out the emission lines, which shows you some of the complexity that we need to include in our modeling. So in this particular, this is the line spectrum as observed, and this is the line as modeled. And you can see that the model has the line in emission, but absorption carves away a lot of that. So what we observe is only that. So if you didn't understand this, you would come to a very different interpretation of the spectrum. And here we have what's called a P Cygni profile, seeing both emission and absorption. If you understand the spectrum, and this is an example of the best spectrum ever obtained in the X-ray band for an active galaxy, from a 900 kilosecond observation with Chandra, you can see the very wide range. So on the top panel and the bottom one, you see an enormous number of iron lines and neon lines and aluminum and magnesium. So you can understand why we need these very complex atomic physics codes to interpret these lines. This also shows you the importance of high resolution. If you made the resolution a factor of 3 worse, all these things would sort of blur together, and our information on velocity and energetics. So it turns out the relative importance of emission and absorption tells us a lot about the geometry of the world. So here's an example, just for those who want to interpret the spectra, of the effects of photoionization. U is a free parameter for photoionization models that is sort of the equivalent of temperature for collisionally ionized. The variation in U tells you variations in how the gas. So for example, for U equals 0, the gas is basically not ionized at all, and you get absorption only from cold material. For U equals 0, the gas is more, log U is 0 now. This is U equals 0. Gas is more ionized. Log U1, gas is more ionized. And then here at log of 2, the gas is almost totally ionized, so the lines disappear. So it's an example of the complexity. I'm supposed to talk for 45 minutes, so I went a little bit long. So what do observers want? How do we get access to this information? So we need tools to find and measure the emission and absorption lines, which are robust and easy to use and understand. And we need to model the continuum FEC. Once we get these lines, we need cookbooks or manuals, or hopefully someday, maybe tomorrow, software to interpret this. What is the temperature that comes out? What is the abundance that comes out? And then we need guides to the models which converge rapidly and stably. And this works already for collisionally ionized plasmas, but photoionized plasmas are more complex. And at least last time I looked at this, the tools were not converging so well. So we'll call these, it's a little joke, a guide to the perplexed. So I showed you a set of complexity and absorption. Here's now complexity in emission. This is the spectrum of Capella, a fairly bright star. And you can see the very large number of lines. And you can see which elements produce most of these lines, rather than label them. So that's high resolution spectra. Like I said earlier, most of our spectra are CCD quality spectra. And so here's a simulation to a very high signal to noise spectrum of a cluster of galaxies using the Chandra ACIS detector. And you can see this is the iron helium-like complex. But this is what the spectrum looks like in reality. So can we really trust going from here to there? That means we have to trust the model enormously. So that's something we have to think about in interpreting the spectrum. So if you have high quality data, as we have for the Tomy Perseus cluster data, and I skipped over that, we can end up with extraordinarily precise measurements. This is abundances in the Perseus cluster from the Hitomi data. And we end up with roughly 5% statistical accuracy, which is incredible, well, extraordinarily good. That requires a combination of high resolution, good modeling, and good signal to noise. Okay, so now that I've run out of time, so I'm supposed to talk for 45 minutes, is that correct?
Yes, but I think that we don't have any other talk afterwards, so feel relaxed to
Okay,
talk
well,
longer.
you just tell me when to stop talking.
I'm not that strict, Chair.
Okay, so we all know that this is Keith, I'm sure went through this in detail. This is taken from a slide that Keith Arnaud made a few years, well, more than a few years ago. So first we have to define the model, obviously, which we're fitting, calculate the model, involve the detector response, and then compare with the data. And I'll say here lie some problems. So I'm going to skip over a bunch of the problems with supernova remnants and continuum fitting and focus on fitting an X-ray binary. It's a black hole binary. There's a paper by Tim Coleman. This is a very bright object, has incredible signal to noise. So this is a small chunk of the spectrum. This is 1 angstrom wide. These are some of the models that Tim has fitted to the data, photoionized models. The red is the fit, the black is the data. And so these are some of the models. I'm not going to go through the details of the models, but they're all involving photoionized gas, which also has a black, some cases a black body, and absorbed along the line of sight. So notice here, model 4 has these 3 parameters. It has 1 photoionized gas. This model has 2 photoionized components. In this model, notice that the chi-square and the degree of freedom. So these are terrible fits to the data in the chi-square sense. But why are they terrible fits to the data is extraordinarily subtle. The signal to noise is extremely high. And you have certain places in the spectrum which are simply not well fit. And it's the question is, what are we learning? Is chi-square a reliable indicator? What should be ignored and what should not be? Are we missing fundamental information by not fitting these lines? Or are these simply errors, quote unquote errors, the wrong word, atomic physics parameters that are not well determined, or subtle physical features which are simply not important? So what do you do when you have a spectrum, when you have this, in the chi-square sense, really bad fits? Notice the giant change in chi-square, 10,000, by adding basically one more parameter, which turned out to be adding a disk black body to the continuum fits. So this is a real, I think, a challenging issue in the future. So, question is, what is in the bottles and what is not? A famous quote is, how do we know what we don't know? What is real and not real? So I mentioned Tim Coleman directly, he's the only name so far. In this paper, 75 out of 175 lines do not have an identification In other words, in these giant atomic physics tables, these lines are not well identified. That's the main source of the high chi-square. Is this telling us that there's new physics? Atomic physics is incomplete? Are these lines that we should have known what they were, but they're red shifted or blue shifted, so we don't get the right wavelengths? What level of detail do we have to follow? If we're fitting the continuum, we follow every bump and wiggle. So this is a model for another black hole source. Notice the level of complexity, how many different components there are, which are then mapped back to physical objects in the black hole. Or do we have this issue? We have this incredible suite of absorption due to iron lines. This is called the M-shell complex, which are just ridiculously difficult to fit. Atomic physics is more than a little messy. Do we need to include that information, or should we ignore it? Okay. So I'm going to give you a highly biased view of what we need to do before we start using our fitting engines. So you can see my opinion here. So the first thing is find and identify the strong lines. So you need software to do that. Then we need to figure out what are the lines that were detected and can we identify them. We need to figure out problem areas where interpreting information may be very difficult. And then the parameters of lines, the physical width, their equivalent width, the line shape, and the lines are not expected to be Gaussian. Then we need an intelligent user who decides if what they got out was reasonable. So a very intelligent user was Jelle Kostra, who looked at this high resolution spectrum of the Crab Nebula. And what he found was that the lines were in the wrong place. So these are the lines that he was looking for. So look at this in particular. This is from neutral oxygen. So the data are points, and the red line is the model. And whoops, the lines are shifted. If this were an AGN, and I was writing a paper, I would have said, wow, we had large Doppler shifts. Jelle, who knows more atomic physics than I by a lot, was able to show that this is because the oxygen is in dust, not in gas, and the energies of the lines are shifted. So we have to know enough to know when we found something new. So then you got to compare the output with what you expect. In other words, if the analysis of your source tells you it's photoionized gas, and you thought it should be collisional, you have to understand what's wrong. Have we made a discovery, or we just did something wrong? So we need a handbook which describes for each class of sources what sort of things we expect. Or we can have a computer program rather than a handbook. So then we leap and try to determine the physical mechanism and compare that to the expectation. Then get to estimate the free parameters of the model, temperature or abundance. And the reason we need that is, at least so far, the model codes like XSpec really need an accurate seed to start the fitting. Because if you don't have a well-defined accurate seed, the model, the programs, at least in the past, have run off and gotten incorrect results. And then frequently doing MCMC, well, at least in the past, has taken an enormous amount of time. And I'm going to stop there. So thank you for your patience in my running over schedule.
Thank you very much. Questions? So we have on chat.
So this one, I think, is really a question for Keith Arnaud. So I'm going to tell you what I learned from Keith, and then Keith will correct me. in the past, with proportional counters and CCDs, because the matrices that transform from detector units to physical units were not strongly diagonal, you really can't fit in the physical unit space because you can't invert the spectrum. For high resolution spectra, calorimeters and gratings, you might be able to do that. So, Keith?
Mm-hmm. Yeah, okay, Martin says thanks, so he's happy. The answer. Any more questions? On Slack chat.
Yeah, I have.
Yeah.
So yeah, hi Richard. I was curious. So based on this need for high resolution calibration, I was curious what you think, or which future X-ray mission you're most excited about in that sense.
Well, I mean, the obvious next one is XRISM, which hopefully will be launched roughly a year from now. As we saw 5 years ago, with a wonderful spectrum of the Perseus cluster. And we had zillions of spectra of the Perseus cluster, CCDs, proportional counters, even gratings. And yet that first Perseus data set immediately taught us that a lot of the atomic physics in both SPECS and APEC were wrong. Now, wrong is too strong a word. Incomplete is correct. We immediately made discoveries, things that we didn't anticipate, both about the thermal structure and chemical structure of the Perseus cluster, and also about the AGN in it. So I'm very excited about XRISM. It's only flying 20 years later than it should have. Going on to the next step for spectroscopy, unfortunately, I don't see anything in the pipeline until Athena, which is roughly a dozen years away. But a whole area that I really haven't talked about, which is now getting tremendous emphasis, is spectral temporal analysis. My understanding of a lot of the recent papers on X-ray binaries, black hole binaries, and AGN is that some of the degeneracies in the models for fitting the continuum can be broken by doing time resolved spectra. So I think that is going to be, well, it already is in the last few years, will get ever more important. So XRISM and spectral temporal analysis, spectral analysis, I think we'll have to wait a bit for Athena.
Thank you.
And I don't know enough about polarimetry to answer a potential question there.
Thanks.
Maybe a bit related question about the abundances. So, for example, Hitomi showed the abundances of iron that are roughly solar.
Well, it's the ratios that are solar. I went through that plot fast. I skipped over supernova, sorry. These are the ratio of silicon to iron, sulfur to iron, argon to iron. So everything's normalized to iron.
Okay, I see. Mm-hmm.
And so just a comment, this was actually very surprising. There's no reason why the gas in the cluster, which is the integral of stellar processes over a long period of time, should look like the abundances in the sun. The absolute abundances are not solar. The absolute values are third solar, but the ratios are solar. And this is actually very difficult to explain.
Yeah. And also related to that, also you know about the X-ray reflection results, sometimes indicating very high abundance of iron in the central regions. Can you comment on that, whether it would be possible maybe to have such a high overabundance of iron in the cores, or whether it's a spectral degeneracy, or whether also the future missions could resolve that in the course
Sure.
there is overabundance and not in the outskirts of the galaxies or in the gas in the galaxy cluster.
Right. Okay, so just to remind people, when a lot of the reflection fitting, where you're trying to compare the intensity of the quote unquote iron K line to the Comptonization continuum, argues that the line is far too strong and therefore the abundances of iron are high. So how would you check that? Well, first of all, I'd like to see what it looks like with higher resolution data. So we'll just see what happens there. Secondly, the comparison has to be, so if you look at the only other bands we can measure iron in ultraviolet and in the optical. And if you look at quote unquote normal galaxies, you find that the centers are quote unquote metal rich, but 2 or maybe 3 times solar is the maximum. And so 5 to 10 times solar does not seem to be, you can have very high angular resolution in the optical and UV. Of course, you can't get way down near the black hole. But when you look at the optical and UV emission lines, the broad lines and the narrow lines, you don't tend to find very high abundance ratios. So that would require that the gas that's producing the X-ray lines be different than the gas that's producing the optical and UV broad lines, which could be true. It'd be a nice discovery. Third, so higher resolution, direct comparison with the optical and the UV. But finally, there's also a atomic physics solution. Javier Garcia and his colleagues have shown that when you go to very high densities, basically the atomic physics cross sections change in a way that can produce these strong lines. And so he has developed a suite of models which incorporate this high density. And my understanding is that in those models, you don't get the very high abundances. So that would require, if you think about the processes in the disk, the disks are very dense, remember, that the iron K lines are coming from not the atmosphere of the disk, but the thicker part of the disk where the densities are extremely high. Does that help?
Mm-hmm.
So
okay, yeah, thank you.
Ask Javier Garcia.
Mm-hmm. Yeah.
Question by Johannes. Hi, you made an interesting comment about comparing optical to X-ray spectral analysis, and now with Prism coming out, we are getting to higher resolution. And once we get several hundreds of objects, maybe not with Prism, but with the next mission, I was wondering if you expect that we will then all fit multiple Gaussians to the lines and stare at line ratio diagnostic plots like people in the optical field.
Yeah, there's a lot of discussion inside the team. I think at the beginning, we'll do both. We'll look at the line ratios and also do our model fits. And basically check the model fits against the line ratios. The problem with line ratios is that you're throwing away a lot of information. There are many lines, and at least if you look in the optical band, they tend to focus on a small number, which have the strongest lines, or if you will, the most sensitivity to a given parameter. What I tried to show in that spectrum of GRO 1655 is that if you don't include that information, you may end up with wrong results. So I think we're going to, for at least for the first few years, calibrate both. In other words, what do line ratios tell us? And then what do they predict the other lines should be? In which case we'll have to do more global modeling. The second thing is that, as I also tried to indicate with the spectrum which had the combination of emission and absorption, if you're looking at lower resolution data, you just don't see that at all. All you see is this blob. And I expect that an awful lot of the results, naively, I expect for black holes, well, at least for AGN, we already have we have moderate resolution ion K-line spectra for galactic black holes. But I expect there to be a combination of emission and absorption all over the place, just like you see in the wind spectra in quasars. These things called BALs, broad absorption line objects. That's my naive expectation. So I expect a lot of the details of the results to change when we get these data. And so we're going to have to think about how to compare what the high resolution spectra are telling us with the vast amount of CCD and other types of data we've had in the past. Okay.
Okay, if there are no more questions, then Richard, thank you very much for your very nice introductory talk.
Thank you for the opportunity. Hopefully, I didn't confuse too many people. I'm going to exit out of the slides.
Okay, so yeah. So for us, it's a late afternoon. So this is the end of the first day of our workshop. Richard, you have still the morning, so have a very nice day.
Yes, thank you very much.
Maybe if there are some more questions, please write it on Slack and we will answer them or forward them to Richard. So thank you all for the participation today here in the audience, also online, and see you tomorrow.
Okay.
Thank you.